The paper title is Anycast as a load balancing feature, and this paper is from Google. Had no idea about it. You can see the name. You can see the paper on the screen. I've also linked the paper in the description down below. So the title of the paper is Anycast as a load balancing feature from Google. This paper, I checked the ResearchGate website and found out that this paper was published in November 2010. So it's pretty old. This is not something that Google uses today, but it does touch upon some very interesting design decisions that were taken back then. And think of it, it's 2010. The scale is not as high as it is today. So Anycast as a load balancer. So let's start going through this paper. Even I have just skimmed through it once. You can see a bunch of links there, which is open. Try to understand how it is actually practically done. But we'll go through it. Almost I'll be going through it while we are doing this live. So our IT organization, basically Google, is made up of subsystems, each providing a service such as DNS, LDAP, HTTP proxy, and so on. Each one deployed globally using their own replication mechanism. Team provides load balancing and failover services. We recently added Anycast as a service we offer to other teams. So they're offering Anycast as a service. We'll go deeper into what that means. The key reason is they needed to be able to failover between load balancers. So that's pretty interesting. It's more about that, hey, we already have a bunch of load balancers. How do we do failovers across them? So what if one load balancer is down? How do we route traffic to another load balancer? That's what this entire problem statement is all about. While Anycast is complex, now this is a very interesting line. While Anycast is complex and mysterious to many system administrator, no matter how smart you are, it's always a mystery. Our architecture provides the service in a way that other teams do not need to worry about other details. They simply provide the service behind the load balancers they currently use with additional virtual IP addresses. Right? The paper describes how Anycast works, its benefits, and architecture we use to provide Anycast failover as a service. Right? That's the context. So let's diving deep into what architecture of Google was in 2010, the decisions they took, and what they got out of it. So it starts with the most natural way to think about load balancing is to put many service replicas as required in your server room. Service replicas implies, let's say your profile service has multiple API servers. So service replicas is not DB replica. Service replicas is the replica of your services, basically multiple instances of your auth service, payment service, profile service, this service, that service. So that are service replicas in your server room. And remember, Google had on-prem infrastructure, which is why they said in your server room. So they are not assuming you're cloud native, because back then cloud was not even a thing. So keep that thing in mind when we are reading this. It's 2010. And have a load balancer distribute the load amongst them. So load balancer is also in-house. So what it says about load balancing, many service replicas required in your service room, and have a load balancer distribute the load amongst them. To increase reliability, load balancers are usually deployed in high availability pairs. Now this is a very common pattern that whenever we discuss something, hey, we need a standby node. This is a classic case of high availability pairs. So you would never have one load balancer. You would have multiple instances of load balancer. Again, this is not EC2 load balancer. This is not an infinitely scalable load balancer. This is literally one instance of a load balancer. You can see the diagram here. Here there are two load balancers. It's not that this is infinitely scalable load balancer. This is just single instance running, right? And this is high availability pair. So literally two instances of load balancers over here. Load balancers are usually deployed in high availability pair, and we assume this to be the case throughout this paper. A regular load balancing scenario would look like drawing one. This is drawing one. So user through their private network, internet and whatnot, the request comes to load balancer. This is literally a single instance behind which you can see multiple service replicas running. Auth service, two instances of auth service, assume that, right? So this is a very primitive setup. The above is already an improvement in reliability. Why? Because given that you have two instances of load balancers running, one of them fails, the other one can still continue to function. Your system is already having an improved reliability, but it can go further. So they said that although this is good, let's take a step ahead, like let's go a step ahead and make it even better. What problem is it solving then? Although they are having pretty deep reliability, the problem that they're solving here is, imagine a disaster scenario where the users are still active and requesting the service, and so is load balancer, but all the backends of the specific service are not. What they're saying is, what if, assume, let's say a hypothetical situation where here what you're having is Friday evening, let's say you deployed a buggy code and it somehow started crashing your services due to mishap configuration, wrong code, null pointer exception, this and that, right? So what if load balancer is running fine, network is running fine, your infrastructure is running fine, but your backend services is not? So now the high availability of load balancer does not solve this problem. Why? Because you chased reliability, you chased high availability of load balancer by having two machines running. One load balancer, like two load balancers, both are actively working. Right? Now what is happening over here is, they say, what if the servers are down? So even if here you have two instances, it does not matter. Why? Because your service itself is down. Right? So having multiple instances of load balancer servers is not enough to solve this problem. Just perfectly fine. A better design, now, which is what they said, that this solution of having two load balancer servers will not solve this problem. So a better solution would be what? A better design would automatically redirect all those clients to another location or server room. So it suggests that if in a particular server room, when the code was deployed, think of it like a region. In a particular region, when the code was deployed to any region, any reason, that region is facing an issue, that the service deployed in that region is not starting up, configuration mishap, whatever happened, you would want to redirect it to another region. Think of it like region, because you all are cloud native people, then you would be able to relate to that, right? But think of it like one rack not working, you move it to other rack. Or think of it like one site not. So site is a very common word that is used across cloud, where you say that one site is not working, that's why you move it to another site. Now you would want to make this process as transparent as possible, right? Obviously switching from one site to another needs to be made as transparent as possible. A way to accomplish this is to identify the nearest secondary location. That's whole the problem statement is. That one site is not working, your requests are coming, you would want to redirect this to other part so that your system still continues to function. You want to do it to nearest secondary location and configure the load balancer to proxy or redirect all the user requests there until local service is reestablished. Basically, until the site that is down remains down, I would want to redirect the request to other site which is active and healthy, right? Until this comes back up. When this comes back up, I would be switching it back. Right? This is what we need to do. Most load balancing products offer automatic redirection as depicted in the right. Drawing number 3, which we'll take a look here. This is what they're trying to do. This is what remote failover is, right? User reaching out to something that is not working because wrong code is pushed, backends are not working. You would want that request to automatically redirect to another site. This is site 1, this is site 2, site 1 not functioning. You would want this request to transparently, seamlessly move to another site. That's what we want over here. Drawing 3. But what if load balancers are also not available? Right? How can we, like said in diagram 4, this case? So they're not just saying that only the backend servers are down. What they're suggesting is, what if the load balancer on this is also down? Like, why would that happen? Why would like load balancer servers, everything is off? Imagine someone literally plugging out the power supply of that site. Right? Imagine someone chopping off the network cable of that, and this system or this entire site became isolated. Very much like there are hundreds of reasons for this to happen. What if there is a flood in that? Right? And that entire site is submerged underwater. That entire data center server room is submerged underwater. Right? Quite possible. So, which is where you would want this redirection to happen automatically to this other site. That's what you are chasing. Okay. So what it says, how can this be accomplished in the least intrusive way? What does intrusive mean over here? Basically, without any human intervention, like without a human needing to go deeper, opening the console, changing something. What if this failover happens automatically? That's what it talks about. So there are multiple ways to solve this problem. Now let's take a look at how, like in 2010, again, this paper is 2010. At that time, they suggested there are multiple ways to solve this problem depending on specifics of each implementation. So let's start with first one. One possibility would be to update DNS records for the services. So they're suggesting is DNS-based load balancing, which means think of it like, let's say each region has its own interfacing IP address, and you would say that, hey, this service goes over there to this IP address. This service or request from this goes here to this IP address. So you can have different DNS records or one DNS records pointing or one CNAME record pointing to multiple IP addresses. That is one, right? That's an easier way to do it. So users can now reach the service in different locations. So you, let's say, think of, let me be a little more verbose over here, is you have a DNS record configured which says, let's say, lb.payments.google.com, and you configure this in your load balancer, in your DNS service, against which you specify two IP addresses, one for this load balancer, one for this load balancer. Right? If this is down, you change the DNS entry and say, hey, this is down. I would remove that entry from the DNS. So when the next request comes in for lb.payments.google.com, it would be going only over here. That is DNS-based routing, right? And it is very common way to do it. And even today, we all do it. It's very common using CNAME entries in DNS, Route 53 or any like if you are using cloud native, let's say AWS specific, just check out Route 53 how to configure CNAME that points to multiple IP addresses, right? That's all. But now here's an interesting catch with the DNS-based stuff, and that is potentially this DNS update. Basically, what it says is when you pointed this service to go to this site, and now we are changing the IP address, right, to this site. That hey, for this thing, now you'd say, why would that happen? Imagine you are having, let's say, asia.lb.payments.google.com, and then you have america.lb.payments.google.com. You had Asia thing pointed to IP address 1, America pointed to IP address 2, right? But now Asia site is down, right? And you knew it. So what would you change? You would change asia.lb.payments.google.com to IP address of America, right? This is what DNS-based routing is, that you don't change anything. You operate at a DNS level and you just change this IP address. So that request for Asia now also goes over here, right? Now when that happens, now look, it's not easy. It's easy to say, but in real world, what happens is this DNS update can be automated. Obviously, when you see this is done, you can automatically change the DNS configuration and just reload the service, right? But there has to be a mechanism to check service status in other locations and keep track of their state so the system knows where to send users in case of failure. Now here the key thing is, imagine human is not there yet, right? Imagine it's fully automated system. Now what would happen is someone needs to know that Asia is down, America is working fine, so I would need to change, because Asia is down, the Asia specific endpoint's IP address needs to change to America's IP address, right? So someone needs to know. So if you have large number of deployments like this, you would need to, you need a mechanism to check the service status in other location and keep track of their state so that system knows where to send user to in case of failure. Considering that services are sometimes deployed in hundreds of locations, we'll say, hey, why hundreds of locations? Because don't think of this as regions. Within a region, there could be multiple sites. That's why the better word to use here is sites. That, let's say, in one region itself, you might have multiple sites, right? So if you have hundreds of locations, it would not be effective to have a large, to have a central place collecting all the information about services. See, this is a globally distributed thing, right? You would want to get a central place to have the status about all the regions or all the locations or all the sites, which one is available, which one is not, right? Now that becomes pretty challenging. So DNS update mechanism would need to be distributed to as many locations as a service is deployed. Yeah. We consider this as non-optimal solution since there is a possibility to integrate the monitoring and automatic failover in existing load balancing infrastructure. Perfect. Right. Now, what other problem comes with DNS? TTL can also be a burden. Sometimes it is not possible to use a very small TTL, and the time it takes to propagate DNS changes would still be downtime for the user's perspective. This is a very interesting point, that while you detected or while your service detected that Asia is down, you are changing the IP address for Asia load balancer or Asia endpoint to USA. While this DNS propagation changes happen, the request is still going over here, which is from the user's perspective still a downtime. You cannot have very small TTL because then a lot of invalidation would happen and a lot of requests will go for resolutions there. But you cannot have it too long either, right? So which is why still a problem, right? Once the system is back, there is again a need to update a DNS entries point back to it, which is again like your request would take time to go back over here, right? So for some time user would still experience that, but at least you still need to change the configuration if not anything else. Okay, so this is where Anycast comes in. Now, you would have seen if you read if you build a habit of reading paper, you would typically see half of the paper is there to just set up the problem and potential and possible solutions. And then the other half talks about the actual solution, which is why you see why when people spend a lot of time, they spend a lot of time understanding the problem statement, defining the problem statement, understanding existing solutions that they thought about, and then why this makes sense. So it's very important that before you work on any stuff, it's important to understand the problem statement and the constraints really well, right? Because devising a solution becomes very easy once you have the full context. Okay, so basics of Anycast. So this is where actually Anycast comes in. So they talked about one possible solution using DNS. Now the second thing that they're talking about is Anycast. Like this is where Anycast fits in. This is the second solution. Anycast is a network routing technique where many hosts have exact same IP addresses. Here they are using the term host. Think of it like LB servers. Right? So the idea is, what is Anycast? In general, Anycast is where multiple hosts, multiple machines, think of it like multiple EC2 servers, they all broadcast or advertise the same IP. That hey, I am 10.0.0.1. This machine also says I am 10.0.0.1. So then which IP to advertise, it's up to you. You try to keep it unique, but it's up to you on which IP address you want to advertise. And this IP address is then stored in the switches router table or the router's router table and firewall and network switches across, and it maintains a router map for that. Right? So which is why the key idea here is multiple machines are advertising the same IP addresses. Clients trying to reach that IP address are routed to the nearest host. This is what your entire internet is based on. Shortest path first. Obviously, it's an NP-hard problem, but still the internet tries to get from one location to another. Actually, traveling salesman problem is an NP-hard problem, but the idea is you try to find the shortest path with the information that you have. Right. So the key thing is that's how your internet is designed to work. That is this the shortest path? It's based on distance, network congestion, reliability, this, that, many factors are connected, right? So there are many factors that it considers that what is nearest, but this is how your internet is actually working. If these duplicate hosts all provide the same service, the client simply receives the service from the host topologically nearest. It never said distance nearest. It says topologically nearest. It could be anything, right? So the idea is all machines advertising the same IP. Request comes. the route it would take would be the nearest to reach to that IP. That's the whole point. That's the whole game. That's how internet functions. Now, Anycast per se doesn't have the info. Now, this is where the limitation of Anycast comes in. Now, read this very carefully. Anycast does not have information on service-specific health status. Obviously, it does not have. Who has the information if service is alive or not? The actual, let's say, auth service, payment service, profile service. The machine knows if it is on or not. Load balancer would need to know if they are on or not. Anycast is a routing protocol. Anycast has no information that if America site is working or not, or if Asia site is down or not. Anycast has no clue. No clue. Right? And we need to be aware of this, that Anycast is not a health check solution. Not at all. So, Anycast per se does not have the information on service-specific health status, which might result in requests being sent to location which do not have a healthy instance of service running. True. Because it thinks it is routing to America, which is working, but it's not sure. What if America is also down? Right? So it does not have that context. It is then necessary to think about service-specific health checks. If a given service has about 200 different instances, so if a service has 200 different instances, managing health check and border gateway protocol 4 configuration for each of those instances can be very complicated. So health checks across 200 servers, complex, storing it complex, detecting failure is complex and whatnot. Right? So which is where this is what they are doing. Now let's go into Google's implementation from 2010. The idea is not to see that what are we doing today, but the idea here is to absorb, like understand the thought process, different failure scenarios, and how they are and how they solved it back in 2010. So absorb the patterns, absorb the solution, absorb the thought process. Right? So their implementation is very interesting. We use Anycast for failover between load balancing clusters, providing the benefits of Anycast to any service behind load balancers. So it says that it is Anycast as a service. Right? The idea is anyone who wants it gets it. They don't have to do anything, but we'll go into how that system is built. This reduces a lot of network environment complexity given yeah, that's fine. Our solution uses BGP because it allows creation of hierarchy for the route advertising, but other protocols work as well. Using Anycast, there is no longer need for remote failover using proxies, providing a cleaner solution since client connects directly to failover location. Now, this is something that we need to absorb. So what it says, the key advantage of using Anycast is that you no longer need a remote failover using proxies. You're not taking all the requests to the same proxy and then redirecting somewhere else. It is automatically a switch from a non-functional site to a functional site. Right? That's why Anycast was preferred back then. Right? Whilst you lose client identifying information, it also saves the proxy overhead between servers and users. So what it basically says is, because not everything is going through one, it's a seamless switch. It's very easy, very non-complex. It's a very clean solution, right? Because your client connects directly to the failover location. Because there is no proxy that needs to be configured. It's automatically seamless switch that happening from site A to site B. Okay. So our team provides load balancing as a service, making it completely separate from specific service setup. That is fine. Multiple service can profit. Okay, not technical detail. Here it is. Another advantage of having load balancers as Anycast peers. Key thing, right? Load balancers as Anycast peers, which means all the load balancers are advertising the same IP address. They are Anycast peers, which means they are all advertising the same IP address here. Right? Is reduced number of routing changes because load balancer combines multiple instances of service into one virtual IP. Now here, this is another important line. Load balancer combines multiple instances of a service into one virtual IP, which means the servers or the machines running the same service would share the same virtual IP address. That's what this statement says. That has been one of the concerns regarding Anycast deployment. Having load balancer deal with service specific state health checks make it possible to deploy Anycast to not only for UDP based services but also TCP based services. Let's read it one more time. Having the load balancer deal with service specific state health checks makes it so. Here what they're saying is, let's use Anycast to just take care of switching while let your load balancer take care of doing the health checks for it. This decouples the system where Anycast takes care of routing, seamless switching and whatnot, while your load balancer is taking care of health checks and routing the request within that service. Because the thing about this paragraph is all about that what if, hypothetically, what if we expose all the servers and let them advertise the same IP address. Let's not have load balancers at all. They say why to do that? Because Anycast cannot possibly do it, which is why what we actually want is we want Anycast to just having them advertise the same IP, and I would just seamlessly switch from one to another, finding the shortest path there. While I should not be caring what all servers come up and they also advertise the same IP. Let's use virtual IP address behind the load balancer, making it easier for load balancer to route the request to servers and whatnot. And that's fine. And while Anycast takes care of routing across load balancers, right? So they split this into two halves. Right? We configure the network environment. So there is one subset reserved for Anycast virtual IPs. The routers are configured to accept /32 route advertisements in that subnet. Basically, any IP, like exactly that IP being MAC, advertisement in that subnet from the load balancers. This allows the implementation of protection against misconfiguration by using ACLs, which only allows route from a specific subnet, preventing accidental takeover of IP space. Okay. Bit of networking. I'm not a pro in networking at all. I'm still trying to understand. I don't have much clue about it. I do need to explore few parts, right? So I'll be brutally honest over here. I don't know networking very in depth. Have some interest, but not much. Right? But the idea is but basically you don't want accidental IP overtake of this space and all. It just tries to do something. That's fine. Now, let's go into software that they use. A little more practical here. All the load balancers are deployed in high availability pairs. We saw that to protect against single machine failure, because two load balancer servers are needed so that if one goes down, other is there to serve the traffic, the incoming traffic. Not a standby node, but literally both active, because they know where they mentioned it's a standby node. They said it's there. So I'm assuming it's active. For this, we used Heartbeat from Linux HA project. Linux HA, right now the website doesn't even open. Linux HA. I tried opening it, it doesn't even open. So I found this page, Wikipedia page about Linux HA. So what it says is Linux HA or high availability Linux. The project provides a high availability clustering solution for this operating system, which promotes reliability, availability, and serviceability. The project's main software product is Heartbeat. And what it does is it basically does what it says, a heartbeat, right? So when one goes down, other takes its place. That's what it does. Figuring the minimum number of node, Heartbeat can be used to build large clusters with simple logic, resource monitoring. Resource can be automatically restarted or moved to another node or failure, fencing mechanism and whatnot. Basically, what it is trying to do over here is that it is a cluster resource management software. Heartbeat brings network interfaces and backend management software up and down. Basically, attached to a load balancer and maintains Heartbeat within load balancer and most probably within the service itself. Who is up, who is down and all. But definitely on the load balance, the actual load balancer that when one is down, other takes its place. Right? For backend monitoring, it definitely does that actually. Heartbeat brings network interfaces and backend management software up and down. So this is basically load balancers, high availability of load balancers. Right? For backend monitoring and failover, which means when service go down, they use ldirector D, Linux directory. So ldirector D runs health checks against the backends for each of our VIPs, virtual IPs, adding or removing from load balancing pool services instance that changes the health state. It can also redirect to connections to different location in case of failures of in all backend and using a fallback option. So what they did is this. I by the way, I found this very interesting website, Listnet, and it actually has a an article about configuring a load balancing cluster with exactly heartbeat and L directory. I just stumbled upon it some time back, right? But they have given actually step by step on how to do this. It's pretty simple. It looks pretty simple setup. Go through it if you are interested on how to configure, what to configure, what exactly would change, how it would route the traffic. It has a lot of interesting stuff. So if you want to play around with this configuration, just spin up a couple of EC or two or three EC2 instance and just do this. It's very interesting. It's from Listnet. Just do a Google search. Setting up a load balancing cluster with heartbeat and L directory. Okay. We added a feature to L directory implementing a fallback command when the last of the local backend goes down. So L directory is detecting if the backend is down. When the last of the local backend goes down, which means the site is now completely down, it triggers this command, which is the fallback command, which basically updates that, hey, this site is down, route to other place, right? So it triggers this command. We use that to bring Anycast IP addresses up and down based on the backend status. So that load balancer, now here, who is advertising this? Load balancer. Who is advertising the IP? Who are Anycast peers? The load balancer. So you need to detect if one of the backend, if all of the services are down. If it is down, you say that this is down. So you stop broadcasting this IP address. Right? So not broadcasting. You stop advertising this IP address. Right? So this is what they implemented. Like Google, the folks from Google implemented this. Now, L directory communicates directly with IP config to bring IPs up and down, the local IP config that you have. IPVS is IP virtual server to add and remove packets. Now, what is this IPVS? Let's go through that. This is IPVS. Now, IPVS is a transport layer load balancing, L4 load balancer, usually called layer 4 LAN switching as part of Linux kernel. It's something that comes within Linux. So that server can itself, like the server, if you configure IPVS, that in itself would do balancing across the configured instances. I think here also we have it. IPVS, yes, here also we have it. There are settings. I went through it, installed. See here. So it said this is my IP address and these are my backend servers. See, the real equal to this real equal to this, these are backend servers that are there. 10.8.8.48, 10.8.8.49. This is where it goes. lbcheck.html is what it checks and it sees if it is alive or not. So what it says is that here IPVS is incorporated into Linux virtual server where it runs a host and acts as a load balancer. This is your load balancer. So IPVS admin runs within your load balancer, right? And this is actually your layer 4 load balancer, which accepts the request, routes it to the backend servers, right? Round robin, whatever algorithm it wants to use, right? IPVS can direct request for TCP UDP based services to real servers and make services for real servers appear as virtual services on a single IP address, your load balancer's IP address, right? That's what it does. And how do you configure this? This is how you configure this. That this is my IP address and these are the two IP addresses behind me. So IPVS is your load balancer. So to run your load balancer, you just need to run IPVS admin. Like, might be like better tool would be there now, but this is what it is as per the paper. IPVS is a Linux kernel module for load balancing. It currently supports tunneling, half network address translation, and direct routing modes. No idea what that is. I know network address translation. I have no idea what direct routing DR mode is. In our setup, all VIPs are configured using DR. No clue, right? Then there is some tool called Quagga. It's a network routing software allowing Linux systems to participate in network routing protocol. No idea. That's fine. It's okay. We allocate an IP for each service. Now this is where things starts to become relatable again. We allocate an IP for each service and create a standard configuration for Linux virtual server to bring the VIPs up, and use the feature we added to L-director D to bring the Anycast IP network interface up and down. Basically, to advertise IP or not. That's what it is talking about, right? And virtual IPs is behind them, depending on the state of the backend, which is fine, right? Now, this is what it looks like. Let me just zoom in a bit. Okay, this is what their diagram is. This is what their flow is. You have high availability load balancer, multiple backend servers, real servers. Now this, what each load balancer would be running, we know that it runs heartbeat. Within the load balancer, it needs to do high availability, that one goes down, other knows about it and whatnot. It does that. L director D to maintain, to see which one of the backend servers are alive or not. That's what we saw there. IPVS is what is real, what is maps to that health check, it does that. Then IP config is the local configuration of this, where it changes the route table and whatnot, advertise IP and whatnot, and Quagga is some software. Right? So this is what their stack is. So each load balancer high availability pair runs this module, right? But I do go through this this website to know how it is configured, in case you'd want to go very practical. I'll try that if I find time, but that's pretty interesting. I actually found that exact same setup there. Right? Okay, now what it says. Adding new services to the setup. Now this is where because remember they provided Anycast as a service. So what if Google spins up a new service? This is again 2010, not relevant today, but in 2010. Services can be added to Anycast by simply configuring their backends in a virtual IP on an Anycast enabled load balancer. In this, basically the setting, the file that we saw here. This thing. You just change this configuration. That's all you need to do, right? The network configuration will already be in place, significantly reducing the barrier of entry for new service, because network is already configured. We are just attaching virtual IP to that service. So each, let's say payment service gets one IP, like one virtual IP, auth service gets one virtual IP and whatnot. That's what it seems. In my understanding, might be little here or there, but that's what it seemed while reading. Expanding a service to new location follows exactly the same process. Anycast routing will take care of sending user traffic to new, nearer load balancer setup. Right? Services currently using the setup: DNS, HTTP proxy, Redis, Web SSO, NTP, LDAP. LDAP is in test now. So back in 2010, Google would have been just like 2 years old or something. Yeah, 2008 Google setup, like to Google. I don't know, 25 years it has been. Wait, let me do it. 2023 minus 25, yeah, 2008, right? No, sorry, 1998. Oh, it has been 10 years, 12 years then. Okay, right? All the mentioned recovery times, okay, failure modes and recovery times. All of the mentioned recovery times take into consideration our specific Anycast deployment. Environments with different timeouts and configuration parameters can have different response and recovery time. The route propagation time is less than 1 second, and we can have 30-second dead timer for routers to consider BGP peer dead. Basically, not being able to do it, this is where you would set a time that, hey, after what time you would consider your load balancer dead, your service dead. BGP basically implies your service is dead, not. Cleanly stopping the BGP peering service creates an outage of less than 1 second for the services as the routes update. In the case of all service backends becoming unavailable, it will take the service specific health check time plus less than 1 second route propagation delay for recovery. So time to know that your backends are down plus route propagation delay. So it's pretty less, like 1 or 2 seconds. You see 30 seconds for that to propagate. So at max the outage, when you discover it, the flip happens within a couple of seconds. That's what we see over here, right? Less than 1 second here, less than 1 second over here. And you're considering dead timer to be 30 seconds, which means after 30 seconds, you can consider your peer is dead. Pretty solid. In a sudden network or power failure at the location, it will take time for the dead timer to expire. So 30 seconds when the entire site is down, 30 seconds plus a small route propagation delay for recovery, less than 1 second. So 32 seconds it would do that switch in case of an entire site outage. Pretty solid, right? In conclusion, moving Anycast routing configuration to a managed load balancer service minimizes the work and complexity required for service configuration while providing them with fast, automatic, distance-aware failover. So it just abstracts out the complexity of having regionalized failover or site-based failover. Pretty neat. It also helps reduce load and complexity of network infrastructure because now every team does not have to do that. It's something that has been abstracted. Now people just need to pick a virtual IP for their service and just get few files configured, right? And you are pretty much sorted. By aggregating service advertisements into one peering point per site and reducing the rate of routing changes to complete site failure. So again, not every backend server needs to advertise the same IP. Only the load balancers are part of Anycast IP or Anycast peers. While behind this, it becomes a BGP and the way it runs it. Right? Pretty interesting. And references. These are references. The website is not even opening, but that's fine. Few interesting things. Do go through this page if you are interested into knowing how to actually set it up. Setting up a load balancing cluster with Heartbeat and L directory. And through this only I got to know how it is called because my concept was still little hazy. But here you can see real servers are your actual auth service, payment service, and whatnot. They get their IPs 10.8848, 10.8849, and this is and these are your load balancer, backup router, active router, your load balancer, and they both have different physical IP address 10.8846, 10.8847. Virtual IP is same 10.8845. This both are given the same virtual IP. This is what is maintained by L directory and Heartbeat. So Heartbeat is happening between them, what I just explained, and the router routes the request over here. If one goes down, other takes its place. That's where virtual IP comes in, right? So this is what virtual IP is, the physical IP over here, and the response is directed back to that. So this diagram helped me understand where Heartbeat lies and where L director D lies, right? So do go through that whenever you find time, and the way you can configure is right here, right? So go through it, and this is where how you configure it. So this website seems pretty decent enough that we can try it if you want to. Not sure this package are still supported by latest versions, but if they are, try that out. And here you can see the Heartbeat configuration, dead timer, this no Heartbeat nahi. HS Linux HA configuration, dead timer, this that. Then you configure your IP tables to point to this. Ekdam proper detailed step by step this person has written. Pretty interesting, right? So just go through that to understand how to actually configure it. But this was pretty interesting paper. Did not expect, like, it is November 2010 when this paper was written, right? And how they abstracted a bunch of things out. And again, to iterate, the paper is Anycast as a load balancing feature. I've attached a link to the paper in the description down below. In the description, you'll also find a link to a Google form, and that Google form is all about what topics you want me to cover. I've been doing this for 4 or 5 weeks now. It's just fun, like just click record and start reading papers and blogs and whatnot. Last week we did cap theorem. This time I picked up this paper, and I'll continue to do that. By the way, I picked it up from that list of topics only, where one of the person wrote, "Can we talk about Anycast and how that setup would work?" What you covered in Dukan's podcast. I'm like, why not? So that's where I stumbled upon something little more credible, which is where I stumbled upon this paper. Hey, let's cover this, right? And yeah, this is what I covered, what I wanted to cover for today. Yeah, hope you found it amusing. But I love reading papers. I try to be as hands-on as possible, creating prototypes. We don't get time to create prototype for this, but it's pretty fascinating. The site I've mentioned over here, just use this to set things up on there, right? And try that out. So, superb. That's all what I wanted to cover in this one. I saw an interesting question. I don't know the answer to that on how that works. Again, I said I'm very naive with networking. The question was uh, by Suraya Revan. How can we prevent someone else from advertising other person's IP? I don't know this yet. I have no idea. But this is a very interesting question. Try asking ChatGPT or Bard to at least get um, some pointers on what to explore. But this is something that I'll take. Uh, but I'll try to find it. If I can find something interesting about it, I'll definitely make a video. But pretty interesting. I like this. Chalo, superb. Thank you so much, folks, for tuning in on Saturday evening. I'll upload the recording. I'll edit this video a bit and upload the recording on the channel. Chalo, superb. Thank you so much, folks. Have a great evening. Have a great Sunday. Bye bye.